Hello and welcome. My name is Elhelw. One of the first videos that I did on this channel is when I talked about the relational model, and we explained what the relational model means in the sense that it is a way to represent the data conceptually in a format that looks like a table, where each table represents a type of entity or a type of object. For example, you might have a table about courses, table about employees, table about students, and so on. This table has a schema, which basically is a set of columns or attributes, and then each object or entity that belongs to this table or that belongs to this entity type. In this example here, if you have individual courses, so each entity of these is basically a row in that table, and it has values corresponding to the various attributes or columns. This is a conceptual way to visualize the data or to deal with the data. Knowing that representation makes it easy for us to, first of all, to conceptualize what the data looks like, and also makes it easy to perform operations on this data to produce another forms of relations or tables and so on. What the relational model does not tell us is how the data is physically stored on disk. This is a conceptual model, not a physical model. So you can store the data on disk in any way that you like, or any way that is beneficial or helps the performance and so on, as long as you can still visualize it or conceptualize it in this way. So this kind of leads into the next question of, okay, well, now knowing this, how is the data actually stored on disk? Again, for those of you who have been following my channel, I did a couple of videos in the very beginning about data storage and how the data is physically stored on disk. So if you have not seen those, please go take a look, because it will give you a lot more detail. But let me go through a very quick recap of the important parts that we need for today's video. The data of a specific table or relation is, first of all, everything on disk is stored as files. So this table will be stored as some database files. Depending on the database system, some systems put every table in a single file. Some systems may spread a table on multiple files. Some systems may put all the tables in one file. So there's different way of splitting the data across files. But in the end, you have a bunch of database files, right? Now, a file is usually pretty big. You cannot deal with this file as a whole. Like if you want to read something from this file from disk to memory, or you want to write something into the file, you're not going to treat the whole file as one big chunk or one unit. So usually a file is split into smaller units, which are referred to as blocks, or in most cases when we're talking about databases, these are referred to as pages. So a page is a part of a file, a block of data. This block is usually treated as a unit in terms of reading and writing. So whenever you try to read something from that file from disk to memory, you're going to read a whole page. When you want to write something from memory to disk, you're going to write a whole page, and so on. Now, each page has a bunch of data in it. So usually the data is stored inside the page as, there's usually some header that has some metadata. Again, the details of that you can refer back to the storage videos. And then you have, the actual data stored in the page. When we talked about this, it was in the form of rows. So each row from the table is stored contiguously within that page, followed by the next row, followed by the next row, and so on. Again, there's multiple ways of storing the rows inside the pages, but the bottom line is that the data that belongs to a given row is usually stored together in a contiguous space within that page. So if we want to look at an example, this is a table that represented as this way in a relational model. This is like a table about employees. You have, for each employee, you have ID, first name, last name, phone number, and so on. So when we talk about the model that we just described, all the data that belongs to this first row would be stored together on disk within a given page. And then all the data that belongs to the second row will also be stored together, and so on. So depending on the size of the page, depending on the size of each row, you might have different number of rows per page. If you have small pages and very big rows, you might have just one or two rows. If the pages are big and the rows are small, then you might fit a lot more rows within that page. So just to conceptualize this, again, give some example. Let's assume these are the data pages that we're talking about. And suppose that the size of the pages allows us to only store, let's say, 2 rows in them. So in the first page, you're going to see the data of the first 2 rows. Again, the first row has all the data from that row. So you have the ID, first name, last name, phone number, hire date, job title, department, and salary. All of the data of the first row stored together in that contiguous space within the page, followed by the data of the second row, for example. Of course, in reality, there is no separators between the data objects like I'm showing here. This is just like for illustration. Also, there is usually no space between this first and the second row. Again, I'm just showing it here to make it easier to read. But in reality, you would have just the data followed by other data and so on, and then the query engine or the database system is able to know where does the row start, where does the row end. So it will understand that this is the row, and also will understand within each row where are the specific fields and so on. But again, just for explanation purposes, assume that this is what it looks like inside the page. And the same thing applies to the other pages, so all the other rows will be distributed among the other pages like this. Again, the bottom line here, or the main point that we want to take away from this, is that for each row, all the data from that row is stored side by side together. You don't have interleaving the data from the first row with the data from the second row and then back to the data from the first row and so on. This is not the case for the way we're storing the data here. Now, because we're storing the data row by row, this is called row-oriented storage. I mean, it's kind of like an obvious name. The databases that use this technique are called row-oriented databases, or sometimes they're referred to as row stores. So basically places where we store rows of data. Most of the databases that you probably have worked with usually fall under this category. So things like MySQL, Postgres, SQL Server, Oracle, a lot of the famous or database systems that you're familiar with or you may have worked with usually belong in the row store category. The question is, why did we decide, or why did they decide to store data this way, right? Like I said, we have the relational model, and the relational model doesn't tell you how to store the data. So why did they choose to store the data in this specific way, row by row? The reason for this goes back to the history of databases and how databases were used, when they first became a thing. When databases became a thing, the main queries or the main types of things, operations that users wanted to do on databases were stuff like this. Let's say, read all the data of this specific product. So you want to return all the data of a specific product. Usually this data is, in the model that we just described, that data will be in a single row. So it makes sense to store all this data together so that we are able to retrieve it with one I/O operation, rather than having to get it from, a bunch of different places, which will be more costly. You could also want to, let's say, create a new order, create a new, entry in a table and add some values to it. Again, when you're creating a new entry or a new row in a table, you have all the values that you want to insert. So it makes sense to just write them all together in one spot. Again, it makes I/O easier and more efficient. You might want to have an operation that says, hey, return all the employees that satisfy these filters. They all work in the sales department and are hired after this date. So again, you want to read all the employee information that satisfies these filters. So it makes sense that this information is stored together so that it's easier and more efficient to retrieve it. Or you might want to update the salary of some employee, of this ID to 6,000 or something like that. So again, you want to go to the record of that employee, look for, for an employee that has this ID, and then once you find the record, you want to update the salary. So again, it makes sense that this information will be co-located so that once you find it, you don't need to do any more I/O. So this usually was the kind of operations that people would do, which, if you remember, again, we talked about this in a separate video. This is called OLTP operations, online transactional processing. So operations that usually touch a few number of rows at a time. It usually also needs to access all or most of the information for these rows. It could be read or write operations. So for this kind of operation, it makes sense that the data of each row is all stored together. Let's look at an example. Here, select first name, last name, and hire date from employees where the department equals to HR. So you want to get all this information for the employees that work in the HR department. So suppose this is our database and these are the data pages that we talked about. So again, the unit of reading or writing from disk to memory is the page. So let's assume that we don't have any indexes or anything like that. So we're just going to do like a full table scan. So in this case, we're going to read the first page. So here is some IO. The first page happens to have these two rows. So for each row, we're going to scan and check the condition that we have. So look at the first row, department is not equal to HR. Look at the second row, same thing. Go get the next page, repeat that same operation. So again, look at the first row, look at the second row, same thing. Go get the next page and so on. So here, once we find a row that satisfies that filter, so here department equals to HR. So for such rows, we want to return first name, last name, and hire date. And guess what? We already have them. Since we already read that page, since we're already looking at this row, we already have the first name, the last name, the hire date, or any other information that we want to get from that row. It's right here. So we can just return that information right away. We don't need to go and look for that information specifically and do extra read operations or anything like that for this specific row. Of course, we still have to keep scanning the rest of the table because we might find other rows that satisfy the same condition and so on. But for a given row, once we locate it, the information is already there. Of course, if we have an index, this also becomes even faster. If you have an index on the department, which tells us, hey, these are the rows that have the HR value, then we can go directly and read the pages that only have those rows. We can skip any page that doesn't have any of these rows. So the total number of pages decreases, but again, the moment we locate a row, all the data for that row is already there, so we don't need to do any more IO. Let's look at another example. If we want to insert into employees a new record, so we already have a bunch of new values that we want to insert. In this case, it's very simple. Again, if you remember what we talked about in the storage video, to insert a new row, we just want to look at the metadata for that page or the page directory. Find a page that has enough space. We're going to get that page from disk, and then we're going to write all that new information into that page, and then write it back to disk. Of course, we don't have to write it back to disk right away. We could batch some of these write operations. We could keep it in memory for now. Yeah, but that's kind of like the gist of the operation is that you're going to write it in one operation, right? You don't need to do a bunch of different writes in different places because, again, you want all the information for that row to be stored together. So you just do this one write and you're done. It's very efficient, very quick. Now, these are not all the operations that we do in database, especially today. With the huge amounts of data that we're dealing with every day, with the explosion in all sorts of information coming from all sorts of places, a lot more people are doing more analytical queries now. And sometimes they are referred to as OLAP queries, which is not always accurate because OLAP operations are a specific thing, but this refers to any kind of analytical queries in general. Analytical queries tend to look at a huge number of rows, huge amount of data. They're usually read-only, there's no updates in them. And they tend to focus only on a limited number of columns because they're doing aggregations. They want to get the sum of certain kind of data or averages or min and max or window functions and so on. So they're usually concerned about a limited number of columns, but they want to scan a huge number of rows. So something like, give me the sum of all the employees' salaries in the company. Let's say you're a company owner and you want to see how much you're spending on salaries, so you're just going to do return sum of all the salaries. So this needs to scan pretty much all the employees table, but it only cares to look at the salary column. Or something like this, you want to get the highest salary for every department. So again, you need to scan the whole table, but you only need to look at the department and the salary columns. So this is, of course, these are simple examples, but this is a kind of, analytical queries that a lot of people are looking to do. Now, if we try to do one of these queries on a row store, let's see how that works out. So let's say the query that we just saw, select department and max of salary from employees grouped by department. So again, we need to look at the department and the salary from all the rows. So we start by, again, scanning the whole table. First page, we have two rows. We need to look at the department and salary from the first row, and we need to read the department and salary from the second row as well. We don't care about anything else in those rows. We don't care about the ID, we don't care about the first name, the last name, the hire date, any of that. We only care about the department and the salary. We're going to do the same thing for the second page. Again, get the department and salary from each row in the second page, and then from the next page and the next page, and so on. So basically we had to read the full table, all the pages. Imagine the amount of I/O that we did here. It's super expensive, and we actually did not need most of the data. We only needed 2 columns. So clearly this is not the most efficient way to do this. Using a row store, using this way of storing the data, is not the best way when we have queries like this query. So row stores, what you can tell here is that they're not always the best. There are cases where they work very well. There are cases where they don't work that well. So if we want to summarize what we've talked about so far for row stores, the pros is that they are good for queries that read a limited number of rows with many columns or many attributes. And they're good for write operations, updates, deletes, inserts. Again, because they tend to touch all the data or a lot of the data in a given row, and they only touch a limited number of rows at a time. And they're good for those cases because all the data of any row is stored together. The cases where they're not that good is queries that need only a few columns but tend to scan a lot of the table or the full table, which is the case in analytical or OLAP queries. So for those queries, a row store is probably not the best way to store the data. So this takes us to a different technique to store the data, since row-oriented storage is not the best for those cases. Another technique was invented, which is column-oriented storage. As you can tell by the name, instead of focusing on the rows, instead of storing all the data of a given row together, column-oriented storage looks at the data as columns. Before we look at how the data is represented, also let me tell you that the databases that use this model are called column-oriented databases or column stores. Another name that started coming out recently is columnar databases. So if you hear any of these expressions, then you know what this means. Some examples of such systems are Apache Cassandra, Amazon Redshift, Google BigQuery. There's also Vertica. So there is a bunch of systems that use this technique for storing data. Those are usually systems that are focused on analytical queries specifically, so they target this kind of queries, and that's why they choose to store the data in this way. So looking back at our employees table, if we want to store this table in a column store or in a columnar database, how would this look like? So like I said, instead of looking at the rows, now we're going to look at the columns. So all the ID column values are going to be stored together. All the first names are going to be stored together. All the last names are going to be stored together, and so on and so forth. So now we're focusing on each column rather than each row. On disk, again, we said that the unit of storing things is the page. So again, we're storing data in pages, but what is inside the pages is going to be different. So for example, one page is going to have all the IDs, or multiple pages. Like, if you have a big table with lots of different rows, so the IDs are not going to fit into one page. You might have 2, 4 pages, 10 pages, 20 pages that only have ID values, right? Same thing with the first name values. So again, all the first names are going to be together in as many pages as we need for those. And then the last names, and then all the different columns. So each column is going to be stored together in one or more pages, depending on how many pages that we need for that column. And of course, some columns may need more pages than others. If you have columns that have smaller values, like integers, for example, these might need small amount of pages, whereas if you have columns that store strings, these might be a lot more bigger, so they need more pages to store them. Okay, now that we know how the data is stored, let's look back at the queries that we've seen before and see how this would work. So let's look at the query that we had a problem with, this analytical query, selecting department and max of salary from employees group by department. So when we did this on the row store, remember that we had to scan the full table only because we needed these 2 columns. Now, if we're storing the data in a column-oriented fashion, then all we need is select or read the values for the department and the values for the salary. we don't need to read anything else. In this example, each of them was stored in one page, but they might have more pages. But anyway, we don't need to touch the pages that have first name, last name, hire date, ID, or any of that. So we only need the columns that are referenced by the query in this case. If the query has 1 column, 2 columns, 3 columns, we only need to read those. There is something missing though. The problem here is that how do we identify values that belong to the same row? Here we have a bunch of departments and we have a bunch of salaries, but we don't know which one corresponds to which. In row stores, this was automatically kind of like built in the system because all the data of the same row were stored together. Here, that's not the case. So we don't know which salary corresponds to which department. So in column stores, we need to have this additional step or something else to worry about how to connect the values from these different columns. There are multiple ways to achieve this, so I will explain 2 ways here, and then different systems may use any of these. The first way of doing this is using offsets. This works well for data types that have fixed length values. For example, we're talking about integers, we're talking about dates, we're talking about any of these data types that have a fixed length, like 64-bit values, 32-bit values, and so on. So let's assume that we have these columns and they have fixed length values. What we can do is conceptually imagine that we have these offsets, right? From the start of the column. So there is the value at the beginning of the column, the value that is like, 1 value into the column, 2 values into the column, 3 values, and so on. Of course, all the columns have the same number of values. So now if we are, let's say, if we're reading some value from column 1 and we want to get the corresponding value from column 2, knowing the offset of that value from column 1 will tell us, okay, the offset, let's say, is 5 here, and we know the data size of the values in column 2, so multiply 5 by that data size from the beginning, then we know where to look for the corresponding value in column 2, and the same thing in column 3, column 4, and so on. So then we can basically reconstruct or stitch together the original row based on these values. All the values that exist at the same offset belong to the same row. The advantage of this approach is that it's simple to implement. You just need to kind of match these offsets from different columns. You don't need to store any additional information. Again, this is just computation that happens on the CPU side. So this is the advantage for this. One thing that I did not mention here, because we're not talking about today, is that this also makes it easier to compress the data. We're going to talk about compression in a separate video, but know that in column stores, we are also able to do some compression for the data to reduce the data size and also reduce the I/O. If we use this method, this makes it easier to do that compression. The limitations is that this only works with, as we said, with fixed length data types. It also requires that all the columns are in the same order because we're relying on the offset, right? So all the values at offset 5 need to come from the same row. All the values at offset 10 need to come from the same row. So the order of the rows need to be the same for all the columns. We cannot, for example, let's say decide to sort column 1 without sorting column 2 and column 3. Once we decide to sort any column, we need to sort all the other columns by the same, by the same order so that the same elements are still matching with the same offset. So this is another limitation which may introduce some overhead sometimes if we have to do a sort operation, but this is something that we have to keep in mind. Another way of connecting these values is using explicit row IDs. So instead of having these offsets kind of in a conceptual way, this time we have to actually make them more explicit. So again, assume that these are the 2 columns that we have. We might have more than 2 columns, of course. So now we're actually going to add row IDs to each data item. So basically, this happens while we're inserting the data. As we're inserting the data, each row we want to insert, we generate a row ID and put that row ID in all the values of that row. So the data will look like this. So basically, that row ID now represents a row where these values are coming from. And this is duplicated for every column. So let's say row ID 4, meaning that all the values in the different columns that have that same row ID came from the same row. The advantage here is that this works for any data type. We don't need to stick to fixed length because we're not doing this conceptual computation here. the row ID is explicitly stored in the data. A limitation, of course, is that the row IDs are explicitly stored with the data. This means that it actually adds to the data size. Now we're storing these IDs with every single column. The more columns that we have, the more space that we need for the row IDs. So this increases the data size. It also increases the amount of I/O that we need to read the data from. Another thing is that it also limits the capabilities of doing data compression. Again, we're going to talk about this in the next video. Knowing that there's these two methods, we're not going to talk again today about which method we're using explicitly, but just know that each column store has a way of being able to connect different columns and produce data that belong to the same row together. All right, now we already saw how using a column store helps in the case of analytical queries, right? But just for the sake of argument, I guess, what happens if we try to do an OLTP style query on a column store? So like, are column stores good for all types of queries? We've seen that row stores are good for some queries, but not for all. Column stores definitely good for OLAP style or analytical style queries with aggregations and so on, but how do they do against the other kinds of queries? So let's look at this query, the one that we saw in the beginning. Select all this information for employees that work at the HR department. Now, assume that the data is stored in columns, not in rows, right? So here, what columns are we touching? We're touching the department column to check the filter, and we also touch the other three columns that we want to return. So the first thing we're going to do here is that we're going to read all the department column. This, again, could be in one or more pages, right? Now we're going to scan that column, each value, to see which values satisfy the filter. So we're going to scan until, let's say, we find an HR value, right? So when we did this query in row stores, remember, once we found something that satisfies HR, we didn't need to do anything else. Like, all the data was already there for that particular row. The data was already there, so we could just return it. Here, the data is not there. We need to go and read it. We need to go and find the first name, the last name, and the hire date. So we need to read the page that has the first names and locate the corresponding value in there. So we need to do that stitching that we talked about. And we need to do the same thing for the last name, and we need to do the same thing for the hire date. So the more data that we need, the more columns that we need, we're going to need to do more I/O here. So again, this is not the most efficient thing. There's more I/O involved. There's also more CPU involved because we have to do this, matching or reconstructing the rows from all these different columns. So again, this is not very efficient. And of course, we still have to scan the rest of the departments because there might be other rows that also satisfy this filter. So again, there is a lot more I/O in this case. There's a lot more CPU involved as well. So not very efficient with this type of queries. Another example is inserting a new employee, right? Again, here we have all the data of an employee that we want to insert. When we did this for a row store, all we did was just locate a page that has empty space, do one write operation, and we're done. Here, we can't do that because the data is stored as columns. And we have all these different values, and we want to put every value in its corresponding column. So basically, we need to read all the pages, or at least the last page of every column, the page that has space, and then we need to do multiple write operations to add these values to every page and write them back to disk. So again, here the cost of this one insert is too big. Again, so column stores are not the most efficient for this type of operations. All right, so to summarize column stores are suitable for queries that need only a few columns but over a large number of rows. And they also enable to do data compression, which again, we're going to talk about in the next video. But they are not suitable for point queries that read, a lot of information from each row, and they're not great for data writes. All right, to summarize, let's just do a quick comparison between row stores and column stores. Again, the same information that we talked about today, but to put it all in one place. Row stores, they store the data as rows. All the information in every row are stored together. Column stores, they store the information in every column together. Row stores are good for point queries. Column stores are not. Point queries are queries that usually retrieve a small number of rows but need to look at a lot of the data in those rows. Same thing applies to inserts, updates, and deletes, again, because they tend to touch a bunch of different columns or all the columns in a given row. So row stores are good for that. Column stores are not. On the contrary, aggregation or analytical queries are much better done in column stores because they tend to touch a few columns over a large table or over a large number of rows. So then the focus is on reading only the columns that we need. And column stores, last but not least, they support compression, which again, more details on that will be in the next video. Hopefully this was helpful. Hopefully you get the idea of column stores and how different they are from row stores and what is each of them good for. Of course, as always, nothing is always good, nothing is always bad. Each system or each technique is usually good in certain cases but not good in other cases, so it's important to understand what your use case looks like to determine what kind of database you would need. If you have any questions or comments, please let me know. I'll try to get back as soon as I can. If you found this video helpful, please hit the like button. If you have not subscribed already, please subscribe to the channel. And with that, thank you so much for watching, and I will see you in the next video.